Dr. Romano, looks like you're doing chemistry today.
Hi, I'd like to discuss with you a question that most students have a great amount of difficulty with. And this is involving an area of electrochemistry called the Nernst Equation. Whenever we find the cell voltage, also known as the cell potential, we're always assuming what we call standard conditions, which essentially means that if you have a gas, the gas is around 1 atmosphere. If you're having concentrations, everything is at 1 molar and the pH is 7. But in real life, these type of conditions are very difficult to attain. And therefore, when you calculate the cell voltage, you don't get an accurate reading. So in order to compensate to that, the German chemist Walter Nernst came up with an equation to take into account concentrations of different ions at different pHs. Let's have a look. Now, what we're going to do, it looks a little scary. We're going to look at the Nernst equation. It says that the cell voltage E, and this E stands for the voltage at non-standard conditions, meaning you're not at 1 atmosphere. The pH is not 7. The E is equal to the E0, that's the voltage under standard conditions, minus 0.6 log of Q. The N is going to stand for the number of electrons transferred. I'll show you a little trick on how to get that in a second. The Q is going to equal the equilibrium constant. And as you know, at equilibrium, the equilibrium constant is the ratio of products over reactants. All right, let's do an example. I'm going to give you 2 half cell reactions. Copper plus 2 electrons gives copper, and the voltage is 0.34 volts. Zinc plus 2 electrons gives zinc, negative 0.76 volts. What I want to do is to find the E for this reaction. Copper plus 2 plus zinc gives zinc plus 2 plus copper. But here's the deal. I give you the copper at 0.01 molar, and the zinc is at 1 molar. The minute you see an ion concentration not at 1 molar, you know it's the Nernst equation. So the minute you see concentrations are given, you know it's the Nernst equation. Let's first get the E0. Here's a nice little trick. Copper plus 2 is on the left side. Here, it's on the left side. So that means we're going to keep the 0.34. If you go to here now, the zinc is on the left side. Here, the zinc is on the right side. So you're going to reverse the sign. So it's going to be the 0.34 plus the 0.76, and that gives me 1.10 volts. All right, up goes the Nernst equation. E equals E0 minus 0.6 log of Q, which is the products over the reactants. You're not using solids, of course. Solids equal 1. So it's the zinc plus 2 ion divided by the copper plus 2 ion. Okay, the N is going to stand for the number of electrons transferred. Here is a 2 and here is a 2, so therefore N would equal 2. If this was a 3 and this was a 2, you use the least common denominator, which would be a 6. If this was a 5 and a 2, the least common denominator would be a 10. So we're going to plug in. We know the E0 is 1.10. We just calculated it. There's the 2. The log, we know the zinc is 1 molar from here. We know the copper is 0.01. Bring it down. 1.10. 0.06 divided by 2 is 0.3. 1 divided by 0.1 is 100. Log it. Log of 100 is 2. I show you very clean work. The arithmetic works out to 1.04 volts. You might be sitting there saying, well, 1.1 versus 1.04, it's not that big of a difference. It's not a big difference in the sense of a real-world answer. But if you were in a chem lab, it is a big difference. So there is a voltage difference when you take into account the ions, even though when you look at it and you thought in terms of money or something like that, it's not a big difference, 1.1 versus 1.04. But in chem, it's a big deal. So the bottom line is, you now know how to deal with, if you see concentrations, you're going to be using the Nernst equation.
Thank you, Dr. Romano. If I know this, will I get a 30 on the DAT?
Probably not. But nevertheless, make sure you understand it and use the new edition of our book. I have all the new problems in there. Good day to you.
Okay, Dr. Romano, I am. Nernst Equation. Wow.